Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper from the Hugging Face trending list, published on November 27, 2025, about 6 days ago. This paper introduces a memory-guided navigation system that combines a sparse global map with geometry-aware local control to achieve state-of-the-art zero-shot visual navigation that stays reliable even when indoor scenes change. The paper is titled MG-Nav Dual-Scale Visual Navigation via Sparse Spatial Memory. And, as we will see later, the mix of compact memory and strong local control leads to some really promising results for robot navigation. Figure 1 shows how the system turns high-level visual navigation into two coordinated parts that resemble how a person explores a house. The left panel illustrates the raw visual navigation problem, where the agent must reach an image-specified goal from an initial observation. The middle top panels depict global planning that uses a sparse spatial memory graph, which stores only key regions instead of a full dense map. The bottom row contrasts local navigation. Methods with occupancy maps often collide with new obstacles, while the human-inspired and MG-Nav approaches adjust paths smoothly as the scene changes. Figure 2 explains how the memory-guided system actually runs navigation, showing how global planning and local control cooperate. The large top panel illustrates the sparse spatial memory graph, where each circle marks a region node connected by traversable edges and enriched with keyframe and object embeddings. The lower left panels detail global planning, which matches the current observation and visual goal to graph nodes through keyframe and object retrieval. The lower right panels focus on local navigation, where a geometry-enhanced foundation policy uses those waypoints to generate smooth trajectories, avoid obstacles, and visually align with the final goal, with global planning and local control running at different speeds. Figure 3 explains how the sparse spatial memory graph is actually built from raw exploration data. The top row shows an exploration tour converted into region nodes using farthest point sampling, then linked into edges based on how the robot moved through time, so every edge corresponds to a feasible transition. The bottom row details how each node stores information. Keyframes are selected for diverse viewpoints, while segmented objects are turned into compact feature embeddings that record what is present in that region. Table 1 shows how different navigation methods perform on the HM3D instance image navigation benchmark, and it highlights how much the new memory design helps. The upper block lists foundation models without any explicit memory, and they reach success rates below about 25%. The middle block lists reinforcement learning methods, which still stay far from reliable navigation. The bottom block lists memory-based systems, where methods using dense scene maps improve performance, but MG-Nav, with its sparse spatial memory graph and only RGB input, achieves the best success rate and path efficiency overall. Table 2 reports how well different navigation methods handle image goal navigation in the MP3D dataset, and it shows that the memory-guided approach clearly leads the pack. The upper block lists foundation models without memory, which stay below about 16% success rate. The middle block covers reinforcement learning-based methods, which reach around 78% success, but with less efficient paths. The bottom row highlights MG-Nav with its sparse spatial memory graph, which attains about 84% success and the best path efficiency, using only RGB input. Table 3 highlights which ingredients of the navigation system really drive performance. The top block on components shows that adding the sparse spatial memory graph nearly triples success, and the VGGT adapter then adds a smaller but meaningful boost. The middle retrieval block indicates that combining global keyframe matches with object matches works best because it joins coarse scene recall with fine object discrimination. The bottom graph sparsity block shows that moderately dense graphs give the highest success and path efficiency, while overly sparse graphs hurt, especially the path length metric. Alright, wrapping up, 2 takeaways stand out. Sparse spatial memory plus geometry-aware local control gives robots strong long-range planning without heavy training, and this design delivers state-of-the-art, zero-shot navigation that stays reliable when indoor scenes change. The broader implication is a more practical path toward everyday home robots. That is it for this episode of the AI Research Roundup. I am Alex. Thanks for listening.